Good morning, everybody. I'm Marco Zuppelli, and today I will present you a tool that we developed that helps the investigation for network covert channels. So, first of all, stego malware is an emerging class of threat that uses information hiding and steganography techniques to conceal its presence within digital objects. Digital objects include images, audio files, or network. Stego malware can, for example, implement stealthy multi-stage loading or escape security perimeters. Among the all different techniques that stego malware can adopt, the usage of covert channel is of a prime importance. Through these techniques, it is possible to orchestrate botnets, exfiltrate information, or, for example, configure backdoors. This work is focused on the usage of network covert channels that are hidden paths that exploit traffic and trafficked features to enable remote endpoints to secretly communicate. There are two main types of network covert channels that are storage, where the information is directly stored in packets, for example, into the unused header bits of some protocol, or timing, where the information is encoded in a temporal behavior of the traffic, for example, in the interpacket time. This work is focused on the usage of storage network covert channels targeting IPv6 header. In particular, we exploit three different fields of the header that are flow label, traffic class, and hook limit. So a covert sender is able to modify one of these three fields in order to contain some secret information, and the covert receiver is able to retrieve this information and collect the secret. There are many challenges to deal with when we want to investigate the usage of covert channels. First of all, the carrier is unknown a priori. So, for example, the investigation on the hop limit is different from the investigation of traffic class. And also, it heavily depends on the used technique. In fact, storage covert channels require a different investigation respect to the timing covert channel technique. Moreover, security tools out of the box rarely consider this type of threat, and to write rules that are able to detect, are able to deal with these with covert channels requires non-negligible effort. Also, it typically is not possible to write rules for IDSs or firewalls that are based on packet. So there is the need of a unique framework that can be extended in an easy manner in order to deal with multiple types of covert channels at once, and that supports the collection of network data for threat intelligence. We identified the technology that can mitigate these problems in the extended Berkeley Packet Filter, or eBPF. eBPF is a technology that exploits code augmentation features of the Linux kernel and allows to execute programs within the kernel without changing its source code. Programs are executed once certain hook points are hit, and there are several hook points already predefined, such as system calls or network events. Moreover, there are several toolchains that helps developers to write and inject eBPF programs, such as BPF compiler collection, which is the one that we used. And it is a simple Python interface that eases the entire process of eBPF write and inject. So once the program collects all the information that we are interested in, it writes all the measurements into what are so-called eBPF maps, that are data structures, which are then periodically read in the user space to be processed and parsed. So the main idea, the main approach is to organize the BPF map in the following manner. The whole range of values of a given field is mapped into B groups or beans. Beans are equally spaced, and each bean is linked to a counter. So for each packet, the specified field is inspected, and the counter of the corresponding bean is incremented by 1. speaking about the resource consumption in terms of memory, the lower the number of bins, the less is the memory needed. However, a lower B results in coarse-grained statistics that can pose some limits. For the case of flow tracing, the classical approach requires at least 400 of bits of memory per flow, including source address, destination address, source and destination port, protocol, state, and the field that we want to inspect, and a timestamp. Instead, when using the counter-based approach and considering, for example, 32-bit long counters, the memory consumption is limited to 32 multiplied by b. In fact, for the case of traffic class and op limit, where there are only 2 to the power of 8 possible values, and we want to inspect every values, the memory is fixed to 8,192 bits. Instead, for the flow label, we empirically found the rule that the number of B or counters should be at least twice the average number of flows. This results in a really bounded memory. In fact, as you can see in this chart, the classical flow tracing requires a fixed amount of bit per flow, which results in a linear dependence of the memory used and with respect to the number of flows, while our approach is limited. In fact, when we consider counters that are 2 times, 4 times, 8 times, and 16 times the amount of flows, we are able to remain almost every time, under the resource consumption of classical flow tracing. Coming to the bccstego architecture, this current version target IPv6 traffic, and as I already mentioned, we are able to collect statistics for 3 fields of the IPv6 header that are flow label, traffic class, and op limit. We develop programs for the traffic control subsystem, which is able to inspect network packets. There are 2 distinct files, bpfprog.c program, which provide the skeleton of the eBPF program, and the userprog.py, which is the user space utility written in Python. The make file merges the different components and build the IPv6 hstats.py, which is a Python module executable. Through the execution of this last module, it is possible to define parameters such as the number of bins or the interval to read the eBPF map in the user space. To evaluate the capabilities and the performances of bccstego, we prepared a testbed composed of 2 virtual machines which are able to exchange network traffic through a 3rd virtual machine, which act as a router and run the bccstego to collect statistical information. To test the tool in realistic network condition, we replayed the background traffic collected by Kaida from an OC192 link, which is composed of 35,000 IPv6 conversation and more than 1 million of packets. Moreover, to create covert channels, we deployed a covert sender and covert receiver, able to communicate secrets of 1 kilobit and 65 kilobit embedded into SCP traffic. The metric that we choose to use is the number of changing bins between subsequent readings of the eBPF map. In the case of flow label, through this metric, it is possible to estimate the amount of IPv6 conversations. In fact, every packet belonging to the same IPv6 flow is expected to use the same flow label value. So when an attacker uses this field to contain a secret information or an attack, the number of changing bins can change too much, revealing the presence of anomalous activities, as shown in this chart. For this case, the matrix can be directly used for the detection of covert channels. Instead, for the case of traffic class, the number of changing beans is limited to 4 or 5 on average. This means that an attack that targets this field can produce visible alterations unless the attacker chooses to limit the data rate. In this example, you can see that we used covert channels of 1000 bit, and despite its small size, the channel is completely visible. Finally, for the case, we can done similar considerations in the case of op limit. In this case, the attacker should follow the observed average value in order to remain unnoticed. Finally, we measure the resource consumptions of bccstego. The eBPF program is executed only when a packet is processed, so we measure the average latency caused to process the packets, which is equal to 104 nanoseconds. Moreover, we measure the total delay of 7 milliseconds when a file of 1.2 gigabytes is transferred. Both results are acceptable in most of the scenarios and seems to be promising. Speaking about the memory, the shared memory usage depends on the number of beans, and it is equals to 4 kilobyte in the case of B equals to 2 to the power of 8, so traffic class and op limit, and to 8 megabyte in the worst case of the flow label, where B is equals to 2 to the power of 20. Concerning the user space program, the performances are shown in this table. Specifically, we varied the time interval between subsequent reads of the eBPF map, considering 1, 10, and 30 seconds. In this case, the CPU usage depends on this interval, and the worst performance is measured for the case of the flow label with an high value of B, which was equal to 2 to the power of 14. It remains bounded instead for the case of op limit and traffic class, and this consideration can be extended also to the memory usage. In conclusion, we showcased how bccstego can be used to collect network information and store this information in a counter-based data structure, and we showcased that bccstego can be used to define matrix for spotting network covert channels. We proved that bccstego is memory efficient and it is designed to be easily extended and modified. Future works aim at extending this tool to consider other protocols such as IPv4, develop accurate detection mechanism, and integrate bccstego with other security tools. Thank you. If you have any questions, please feel free to ask.